So, welcome to this next class. I think last time we were looking at that same thing, A plus B goes to C, it's just that C is intermediate boiling, and so you had to have two distillation columns, right, to do the separation. And we did a light out first train, which means that the lightest component is separated out first. Why did we do that? Well, maybe A is toxic or something, so you want to remove it first, so that this is A recycle, and then you have the product column. In the product column, C is the light component, it goes up the top, B is the heavy component, it goes down the bottoms, this is fresh A, this is fresh B, this is recycle A, this is recycle B, this is product C. Yeah, and if we draw valves on it, I don't remember how many valves, but we can just draw them and see what it. These are the valves. Did I miss anything? It's quite possible I missed something. Yeah, I missed the cooling stream. And in the absence of any other information, let us say fresh A is something that's coming from, okay, we basically said that if we do things this way, this is the total B, control the total A and total B, that takes care of the stoichiometric feed balancing problem. Okay, and the rest of the control system, you have to have a temperature controller here, because if any A leaks down the bottoms, it is going to contaminate your product C, right. So, maybe what we can also do is, we are measuring the impurity. You see, you will always have in an operating plant, product quality is always measured, no matter how hard it is to measure. Okay, maybe it takes 8 hours, maybe you get a reading once a shift, but product quality will always be measured. So, you know how much A is contaminating it, and if too much A is going up the top, you can always adjust the set point of this chap, of the temperature controller. So, what would you do if too much A is going in the product? What would you do to the temperature set point in this column? You will increase the temperature, right, so that A is sent up. Yeah, and so on so forth. Level control, the rest is straightforward actually. Pressure control, level control, sufficient reflux, level control, level control, pressure control. You could have a temperature controller here. You would definitely have a, what does column 2 do? What does the rectifying section of column 2 do? What function does it does it accomplish? Is the question clear? What is the function of the rectification section in the second column? It's a question, please answer it. Make a wrong guess. Of course it does a separation. What separation?
B and C.
I am asking you, the column separates B and C. What does the rectification section do? What does the stripping section do?
Rectification section enhances C.
Enhances C. Well, I don't think that's the correct answer. What does the stripping section do? What does the rectification section do? What does reflux in a column do? And what does reboil do? Reflux prevents the heavy key from going up the top. Reboil prevents the light key from contaminating, going down the bottoms. So, the function of the rectification section is to prevent heavy key, which is component B, from leaking up the top, from leaking up the distillate. What does the stripping section in that column do, in the product column do? It prevents C from dropping down the bottoms. Yes or no? Now, this understanding has to be fundamental. This is, this understanding has to be very clear. By adjusting the reflux, if you increase the reflux, the amount of B going up the top decreases. But if too much A is leaking down the bottoms from the first column, from the recycle column, your purity is going to be off spec. Do you see what I am saying? So, it is not enough to say I want 99.9% pure product. That 0.1% impurity, what is it? How much B, how much A? Okay. The B is being set by the reflux in the second column, the A is being set by the first column. Yeah, this must be understood. If too much A is leaking down, no matter what you do, you have to live with an impure product, because too much A, that leaked A is bound to end up in the top, because it is the lightest component. Yes or no? Okay. So, therefore, I am controlling the A composition by adjusting the temperature set point in the recycle column. I am controlling the B impurity in the product stream by adjusting the reflux. Yes or no? Okay. Now, since degrees of freedom 2 for the 2 each for the 2 columns, that is 4, 2 for the 2 fresh feeds 6, plus 2 for the reactor temperature and level, or temperature and hold up. Yeah. So, that is 8 degrees of freedom. What are the 8 things that the operator is setting? 1, 2, 3, 4, 5, 6. He is not setting the temperature here in the first column, that is being set by the composition controller. He is setting the amount of impurity in the product, amount of A impurity in the product. Does that make sense or no? How many did I draw? 8 हो गई कि नहीं? 1, 2, 3, 4, 5, 6, 7, 8. Degrees of freedom is 8. Operator is setting 8 set points. Yeah. How do we set these set points? Temperature, well, in the absence of a side reaction, you can say, yeah, temperature should be max, because if temperature is max, conversion is max, unreacted A, unreacted B is least. Therefore, the recycle cost, basically the boil up here goes down. Yes or no? Similarly, boil up here will also go down, because there is less B going around. Okay. So, I will say, okay, temperature in the absence of a side reaction, temperature should be max. This is a hypothetical example, we will make a real example just shortly, but I am just trying to walk you through simple rational arguments to figure out how to reasonably specify your what? Your 8 degrees of freedom, your 8 set points. Okay. Level of course should be max, because again that maximizes conversion and therefore minimizes the boil up. So, your steam consumption per kg product goes down. Composition A and composition B set points should sum to whatever is my impurity that is maximum allowed. So, if 99.9%, then mole fraction of A plus mole fraction of B should be 0.1%, right. How do I decide A versus B? Should I have 0.01% A and 0.09% B, or should I have it the other way, 0.09% A, 0.01% B, or should I have it 0.05, 0.05, comparable A and B, mostly A, little bit B, mostly B, little bit A. Basically that is the question.
First of all, we can look on the economics.
Okay, when you look at the economics, what will govern that? Whether you should have, what should be the principal impurity in the product? You got 0.1%. It could be mostly A and a little bit B, it could be mostly B and a little bit A, or it could be 50-50. What will govern that? And I am asking you as an engineer. Of course, I can do an optimization and the optimizer will throw out some, spit out some answers, some numbers, and I can blindly implement them, right. I was a fool before I did an optimization and I remain a fool after I did the optimization, because I did not apply my mind. That needs to be removed.
Ideally, it can be equal.
Why?
So, because in that case, the feeds will be all.
No.
The total mass.
No.
Or it will depend on which one is more volatile.
Now we are talking. Which separation is more difficult? That is what will govern it. So, if you look at your base case design condition, you will essentially look at the reboiler duties. Okay. If the reboiler duties are comparable, what that means is the separation is about the same, and then most probably your optimizer will tell you that look about the same, 0.05% of this and 0.05% of that, maybe 0.04, 0.06, 0.06, 0.0, but comparable amounts of A and B. Okay. If it turns out, for example, let us say that the CB separation is very easy, the BC separation is extremely easy, then what you will have is the product column will have a very low boil up, right. If the product column has a very low boil up, what would be optimal?
Releasing more
Allowing as much A to leak out the bottoms of the first column as is allowable without violating the product purity constraint. So, then my solution would tend towards 0.09% A, 0.01% B, because separating B and C is damn easy. Of course, relative volatility quantifies the ease of separation.
That is also what optimizer will give.
Of course, optimizer will give you something, but the point is you have to look at it and try and understand it, right. Now, after having tried to do that, I have found something, that is what I am trying to impart to you. Okay. So, it all depends on which is the easier separation. It could be both separations are about the same as difficult. It could be that the first separation is much easier, the second separation is very hard, or it could be the other way around, the second separation is much easier, the first separation is very hard, and based on this you will find that your optimizer is going in this direction, or in that direction, you see. And when you have this understanding, whatever the optimizer is throwing out, you will say that makes sense. If the optimizer is throwing out something else, most certainly you will question it, right. And when you try to answer that question, you will figure out whether the optimizer was correct or your thinking itself was flawed, in which case you will correct your thinking, and that is a learning that you take. The point is, you just can't leave it to an optimizer to spit out some result and let it go uninterpreted. Okay. All right. So, what should composition A set point and composition B set point be? That depends on the difficulty of separation 1 and separation 2. Yeah, okay, that takes care of that. What should the temperature set point in the second column be? See, why do you want to prevent C from leaking down the bottoms? Because it unnecessarily goes round and round and round, right? There is a cost associated with circulating something round and round and round. What is the trade off? If you try and do a very tight separation, that means you want essentially no C leaking down the bottoms. What that will do is it will jack up your boil up, because you do not want any C leaking down. As far as you are concerned, 1%, 2%, 3%, 5, even 5% C is okay. On the other hand, if you allow too much C to leak out, you see everything, you see the C will the extra C that is floating around will cause the boil up here to increase, will cause the boil up here to increase. You know, there is a cost associated with recirculating something round and round. Yes or no? So, if you have too tight a C separation, you do not allow any C to leak out, then your boil up in second column shoots up. Okay. If you make it too loose, then again the boil up shoots up, because the flow shoots up, because you know the flow rate, that is the recirculation flow rate, is higher. Yes or no? So, in this extreme the energy cost shoots up, in this extreme also the energy cost shoots up. Surely there is an optimum somewhere. Usually what happens in practice is, you would not like too much C to leak down, because what will happen is this C, once it goes back to the reactor, it can degrade to something else. Usually there will always be some sort of side reaction, blah 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 blah, and that will essentially say, look, you can't have too much C leaking out. Okay. But this is a hypothetical example, we are assuming there are no side reactions. If we assume there are no side reactions and then we try and optimize this process, there is this extreme where the boil up of column 2 shoots up, there is that extreme where the overall energy cost because of higher recycle flows goes up. Okay. There is an optimum somewhere. This, what exactly is this optimum is not clear, you will have to do an optimization. Okay. But from a practical standpoint, there are always side reactions, and because there are side reactions, there is a limit as to how much C you can allow to leak out. Well, you allow as much to leak out. See what I am saying? So, you have a way of setting the temperature controller set point 2. In a similar way, the reflux set point also gets set in the first in the recycle column. You can't allow too much A to get recycled, or too much what should I say, what is the impurity here? C. You can't let too much C in the recycle stream, in the recycle A stream, because that C again degrades to something. Okay. So, whatever reflux is necessary to keep the composition, or to make sure that too much C is not leaking out the top, that much reflux you have to provide. So, there is a reasonable way of fixing the temperature set point here, fixing the reflux there. Now, we come to the last part, total B and total A. How do we fix that? Total B and total A. If there is no side reaction, total B and total A should be comparable. You can't have it equal, because then you are operating on top of the hill, it will either drop down, you know, you are essentially unstable. Okay. So, you would have to be slightly off either on this side or slightly off either on that side, it can't be exactly equal. Okay. Yeah. What does that do? Keeping the A, total A and the total B comparable, given that there are no side reactions.
All will convert to C. So
Yeah. So, it maximizes your conversion, because it is maximizing your conversion, you are minimizing your recycle load. Yeah. So, basically that fixes this and that. If you want, so basically what I am saying is the total A may be kept in ratio with total B, and that ratio set point may be, for example, 1.2, 1.3. Yeah. So, what I am saying is, let us do this. Total A is fixed, and I am going to take this total A. Let us do it the other way, it is easier to draw. Total B is fixed. Okay. I am going to take this total B reading, multiply it by a number which is close to 1, but not exactly 1, maybe 1.1, 1.2, maybe 0.9, 0.8, okay. And that will be the set point for this chap. Now, the operator is setting this ratio set point and the total B set point. Yeah, still 8 things, he is still setting 8 things, but this is a more reasonable way of doing things. It automatically gets you close to, right. Okay. What does this flow controller do? You know, the set point of the B, total B flow controller, this will be used to increase or decrease throughput. Okay. If I look at the reactor, okay, and let us say I increase the B, total B flow set point by 20 or 30%, okay, how does the production inside the reactor increase, or why does it increase? It is very important to understand this. Is the question clear? I am saying I will increase the total B set point and then I will get more production of C. Yeah. My question is why? Why does that? What happens inside the reactor to produce more C? See, production is governed by this equation, rate of generation of C is equal to rate of reaction times concentration of A inside the reactor and concentration or mole fraction of B inside it. This is what governs the C generation rate. So, when I am increasing the total B set point, what is happening to A? See, K is fixed, temperature is at maximum, volume also affects, but volume is also fixed, you are not changing that. The only thing that changes, times V. Total, this is the per unit volume reaction rate, the total reaction rate is this, per unit volume reaction rate times the volume of the reactor. So, volume of the reactor is fixed because I am operating it at max level. So, this is fixed, this is fixed, the only thing that can change is this. My question is, how does it change? Why does it change? Is the question clear? If I put in more B, what happens? The ratio set point will ensure that I am also putting in more A. So, I am putting in more fresh A, I am putting in more fresh B. Okay. I am putting in more. So, the concentration of A and B inside the reactor actually goes up, yes or no? This guy is saying yes, no, maybe.
So, the concentration of the both will be equal to 1.
No, 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 there is also C there, in the reactor there is also C,
Okay. Then
because C is getting generated, right.
So we are putting in, we are also adding to the volume. So
This requires some thought. I knew I will get stuck in this, but what I am saying is correct. I will urge you to think about it, why that is happening. Basically what is happening is as follows here. See, I am putting in more fresh A, more fresh B. Let us say nothing happens to the reaction rate. So, I am putting in more fresh A, more fresh B. C remains the same. Okay. Where does the excess A and B go? It goes in the recycle, right. If it goes in the recycle, my XA, then I am putting in more recycle A, more recycle B. Do you see what I am saying? So, what happens is, essentially because you are getting more total A in and more total B in, XA and XB will increase. There is some C will essentially get diluted out. Yeah. If C is getting diluted out, your XA and XB has increased, therefore, your generation rate of C has increased. You see what I am saying? This is essentially dilution effect. You are diluting the reactant further by putting in more fresh reactant. You are diluting the product out, sorry, you are diluting the C out by putting in more A and B into the reactor.
So
Yes.
Then
residence time will also decrease.
That doesn't matter. Residence time, V is fixed. Look at the expression. V is fixed, K is fixed. Because you are putting in more total A, more total B, it will essentially dilute out the composition of C. XC will go down, XA and XB will go up. So, generation rate of C will go up, even though XC itself has gone down. Do you see what I am saying? This needs to be understood.
So, but then eventually XC will increase.
No, it will not increase eventually. This is what needs to be understood.
So, if generation of
Huh?
Generation rate is increasing, then XC should also
then
increase.
amount of C should also increase.
It will increase, but if you look at this steady state versus this steady state, where total A and total B was small, this steady state total A and total B to the reactor is larger, C would have gone down, XC would have gone down, guaranteed,
So won't it come back to the same equilibrium?
because you are taking out the C, right. There is not an equilibrium reaction, this is an irreversible. A plus B irreversibly goes to C. If it is an equilibrium reaction, we will have a different way of dealing with that. Okay. It is an irreversible reaction, and this is what needs to be understood. If you do not understand this, you can't come up with this scheme. In fact, you can't even tell whether it is self regulating or not. Okay. So, shall we proceed further? So, how is the generation rate being increased? The generation rate is being increased by essentially jacking up XA and XB. Because XA and XB goes up, RC goes up, generation rate of C goes up, however, XC does not go up, in fact it goes down slightly because of the dilution.
So, will the total amount of C remain same, not the
Let us not, we are talking mole fraction. See, whatever C is generated, it is not getting recycled, it is essentially being taken out as product, right. So, C never accumulates. If anything accumulates, it is A and B. C never accumulates, that C is taken out. Yes or no? Okay, so there is no question of C will finally rise, because you are taking it out.
C will rise, the total amount of C should rise a little bit because the generation rate is increasing.
So, the molar flow rate on the exit stream of C would increase. The flow rate of, you are putting in more total A, more total B in terms of moles, molar flow rate of the exit stream will also increase, but the concentration of C would have gone down. But it would not have gone down so much. If you multiply flow and XC, that component flow rate of C would have gone up. That is the extra generation. That is how you are getting more production. Does that make sense or no? Yeah? Okay, once you have understood this, then we can proceed a little further. The other, through very simple qualitative plain English reasoning, now we are devising control systems for something that does not look too simple, at least. Yeah, this approach will work for everything. Systematizing it, maybe I will leave that for a couple of more lectures. You know, what is a systematic way of doing it. I just want to walk you through various examples, so that where I am coming from becomes clear to you. And then when we give you the systematic procedure, step 1, step 2, step 3, step 4, step n, it will be clear what we are trying to do. Okay? All right. By the way, just as an aside, suppose there was a side reaction, and I do not know, well, let us say there is a side reaction which is in series. Okay, A plus B goes to C, C further reacts with, for example, A to give D. Okay, and let us say the volatility of D is the same as that of C, so the D comes out with C in the process. Okay, if that is not the case, if D is heavy, then you need another column to take out the D. Okay, but for this flow sheet, if there is a side reaction, C plus B goes to D, how would you manage this process? you want to minimize the side reaction because C is what fetches you the money. For D, you have to essentially separate it and then process it. You are essentially charged a penalty. Maybe D is a contaminant which is to be disposed of, and there is a disposal penalty that gets imposed. So, you earn money for C and you are penalized for D. So, basically now you want to run the process such that C is maximized and you produce very little D. Let us say B plus C goes to D. This is your desired product, this is undesirable. Okay. How would you manage your reactor?
We will keep excess of A.
Excess of it.
We will keep excess of A. What does that mean about this ratio set point?
X should be greater than 1.
Of course, it should be greater than probably 2, 2.5, 3, 4. That depends exactly on what the kinetics of the two reactions are, but basically you will not be operating around 1, you will be operating around 2, 3, 4. Yeah? No, not depends. That's just the just in the kinetics.
No, 2, 3, 4 depends.
Yeah. So it will not be close to 1.
Yes.
It will be much greater than 1. Yeah. So then this ratio set point has to be much greater than 1. Clear? To suppress the side reaction. What about temperature? Temperature of the reactor.
Depends on both those reactions.
Okay. Now just common sense again. What does a catalyst do?
Decreases the activation.
Decreases the activation energy of the desired reaction. That is what a catalyst is. This catalyst will decrease the activation energy of this, is designed so that reaction A is much more faster than reaction B or the undesired reaction. So basically what that is saying is that the activation energy of the desirable reaction is actually greater than the undesirable reaction if your system is irreversible reactions. Okay. So something follows from this. So energy of activation of, let us say reaction 1 is desirable, will be less than us. Yes, will be less than energy of activation of the side reaction. Yeah. Now we want to figure out how the sensitivity, how to define selectivity. Have you heard of selectivity in reaction engineering? How do you define selectivity? Let us say for the same resistance. So rate of reaction of reaction 1 divided by rate of reaction 2, this is called selectivity, right? Yeah. So how much desired product is being produced in the reactor? I do not know if it is this, maybe it is R1 plus R2, sorry. What will I get? K1 naught is constant,
Minus
I think it will be EA by RT square, and minus will cancel out, times e to the power EA1, okay, minus EA1 by RT times XA XB is constant. Yeah. This guy out here is nothing but what? This is the reaction rate at the original condition. Yeah. So my reaction rate right now is this much. I change the temperature slightly. How does my reaction rate change? Right. So that's the sensitivity of reaction rate to temperature, dR1 by dt. Yeah. So dR1 by dt turns out to be R1. By the way, I am sorry, it is actually this, XA XB is also included. So dR1 by dt is equal to R1 times energy of activation divided by RT square. Okay. dR1 by R1, this is the percentage change in reaction rate. Yeah. Is equal to EA1 by RT square times what? dt. What is this expression saying? If I change my temperature by, let us say, 1 degree Celsius, my change in my new reaction rate R prime will be is equal to R1 plus dR1, whatever it was, plus dR1, right. Okay. So, the new reaction rate or the change in the reaction rate is proportional to energy of activation. Yeah. Now, I know that for the side reaction the energy of activation is higher, for the main reaction it is lower. So, when I change the temperature, my side reaction is more sensitive to a change in temperature than the main reaction. Yeah. So, if right now my reaction rate was X, main reaction, and side reaction was Y, X changes by 2% when I change the temperature, Y would change by more than 2% because its activation energy is higher. Yes or no? All right. So, the side reaction usually will be more sensitive to changes in temperatures. So, when you start jacking up the temperature, your selectivity will actually start going down. Does this make sense? Okay. So, if you have a side reaction, I get back to the same process. If I have no side reaction, T should be max, reactor temperature should be max, maximum allowed. Okay. But if I have a side reaction, as I start jacking up the temperature, the side reaction rate grows faster than the main reaction rate. Therefore, I start producing more D per kg product C produced or per kilomole product C produced. My selectivity or yield to desired product starts to go down. Okay. Okay. So, there is then a trade off. What is the trade off? At lower temperatures, conversion is low. If conversion is low, recycle cost goes up because more unreacted reactant, it has to be recycled. Yes or no? Right. If I increase the temperature too much, I start producing too much junk, right, and that is creating a penalty for me. Between these two extremes, there is some optimal or reasonable value for the operating reactor temperature. Yes or no? So, when you have a side reaction, you can't just blindly keep jacking up the temperature. The temperature should be high enough so that the conversion is not too low, but you can't simply take it to max because very likely the side reaction will start killing you. Yeah. Now, earlier there was some constraint that was saying that look, your temperature of the reactor cannot exceed, let us say, 200 degrees Celsius because the liquid starts to become vapor, you know, you are approaching the boiling point. Okay. So, you can't go beyond 200 degrees Celsius, or maybe because the catalyst starts to deactivate, coke starts to deposit on the catalyst, you really do not want to go. This is a physical constraint. Economic, if let us say we are away from the physical constraint, now an economic constraint is saying do not jack up the temperature beyond this temperature because then you start producing too much junk. Now, this becomes essentially an economic constraint. Okay. The point is, some constraints will become active, whether it is a physical constraint or it is an economic consideration. Okay. Well, why did I say this? Yeah, the point is that depending on the chemistry of the process, it is fundamentally tied to how you set these set points. There is no control theory here. Okay. your reaction scheme, whether the primary side reaction is a series reaction or a parallel reaction, etc., that determines how the hell you operate the process. Okay, so if there is a side reaction, I guarantee you, you won't be operating at max allowable temperature. You will be somewhere in the middle. How much, where, that comes from an optimizer. What should the temperature exactly be? That will come from an optimizer. Yeah. Okay. Now let us get to the next point. Next point is, I want to throw something at you, food for thought. Start again with the tank. We can count the degrees of freedom. Degrees of freedom is 1. By default, I have always been doing this. Yeah, by default I have always been doing this. Can I do this? Is this workable? Is this okay? Will this work? Where instead of setting the feed flow, I set the outflow and then the feed flow adjusts itself. Earlier I was setting the feed flow and the outflow was adjusting itself under level control. Now I am setting the outflow and the feed flow is adjusting itself under level control. Yeah, will this work? Yeah, this is reasonable. This is a perfectly reasonable way of doing it. Yeah, okay. This throws in the question, when should I do this and when should I do that? When should I be having, when does this make sense and when does that make sense? Okay, degrees of freedom is 1 in both cases, or actually 0 in 1 meaning the throughput, how much is flowing through. Degree of freedom is that 1 throughput. Okay. Let us look at a distillation column. Earlier what I was doing was, I was fixing the feed flow rate, flow control, and then I was putting in level controllers and temperature controllers, right? Is that the only way of doing it? Hell no. I could, for example, I could flow control the steam to the column. Maybe I should use a different color for this. This can be blue. Okay. Then I would have level control this way, this level control this way, reflux under flow control, pressure control this way, and I control the temperature this way. So now this is my throughput manipulator. See, earlier I was setting how much is flowing through the column at the feed. Now what I am setting is how much steam I am putting into the column, and that would set how much is getting sucked in under temperature control. Yeah. So the point that I am trying to make is that degrees of freedom is okay. How you manage, the philosophy behind managing those degrees of freedom is also okay, but it is many a times not, you are free to choose where you want to set the throughput. At the fresh feed, you see I could have set the throughput through the column at its feed. That control structure has been drawn n number of times. Yeah. Here I am setting the throughput at the boil up. I could have also set the throughput at the product. Let us say this bottom stream is the product stream and there is a customer who says give me more, give me less immediately. What would I do in that case? What I would do in that case is, this is under flow control. This is the set point for this is coming from the product customer demand. Okay. This is under temperature control, and now the level is getting controlled by the feed that you are putting into the column, right. Does this make sense or no? This is another perfectly legitimate way of running the column. Well, if the level is going down, put more liquid feed, liquid will drop down and the level at the bottom sump will slowly but surely go back up. Yeah, it will work.
But how do you get extra feed?
Because the level is going down, therefore you get extra feed.
And extra feed should be got from the earlier.
Yeah, sure. You
So
see,
there
in a, okay, let's, I mean, it's 10:50, maybe it's time to go, but let me just take a very simple 3 tank process. Tank 1 is feeding to tank 2. This tank could be a plant in itself, and I am talking about the overall material balance on the plant. Okay. Let us say I have something like this. I can do this, set the feed here, and then what I have is level control this way, level control this way, level control this way. This is one way of doing it. Yeah. Here is another way of doing it. Level control this way, level control this way. This will also work just like for a single tank. Yeah. I could also do it maybe this is also perfectly legitimate. So, the throughput in many situations can be set anywhere inside the plant. By default I am saying we will set it at the feed, but in many situations where the feed is a degree of freedom, that means you are free, the throughput is a degree of freedom, you are free to set it, it is not being set by an upstream process. Well, then you can set it at the feed, you can set it at the product, you can set it somewhere inside in an intermediate stream, and a control system can be made. That will work. Yes or no? How do we decide what to do? At the feed, at the outlet, intermediate, where, and how do we go about synthesizing a control system given I am going to set the throughput here. Okay? That is the next thing that we are going to talk about. The point is, the throughput can be set anywhere and you can devise a control system to manage your degrees of freedom appropriately, respecting the overall material balance around the plant, material and maybe sometimes even energy balance.